This is the 4.1 notes. It's an introduction to triangles, and we're starting off with the definition for polygon. This was actually mentioned on a homework on the review last week as well. And so a polygon, here's the official definition. It says is a closed plane figure. It's formed by 3 or more line segments, and it has sides such that each side intersects exactly 2 sides, one at each endpoint. And so we'll write down some examples of polygons and non-examples from this box over to the right. We're going to pick and kind of decide where each one goes, and then as we draw them in, hopefully you'll get a better understanding of each one. So main idea, again, because it's formed by 3 or more line segments, it can't have any curves to it. So that's kind of one more thing if you want to write for yourself, no curves. That can kind of help to eliminate a lot of these ones. So like the circle, that would go in the non-example. The circle cannot be a polygon. This triangle here that is not fully drawn in, that is missing part of a segment. So remember, it has to intersect two, or one at each endpoint, or has to have sides that each side intersects exactly 2 of them. But this right here is kind of missing. So you can't have like breaks in it, like where it's a missing part of it. That would be another non-example. So we'll draw that triangle, kind of missing that part that's connected. Same for this other one, and as I do them, I'll just kind of cross them off like we've already done them. These two, the arrow and the square, both of them can go into the examples of polygons because they're closed. Closed just means there's no openings in them, and they have 3 or more line segments that are connected to create those. So this would be, we could draw this arrow, and also this square. Kind of do those together. Okay, then we have this other, like, it looks like almost it was supposed to be a hexagon, but again, missing part of that. So that would be a non-example because it has to be closed. Something like that. The heart is also a non-example because you can't have any kind of curves to it. Then this one over to the right, if you count it, it's got 5 sides here, or 6 sides. This is called the hexagon, and we are going to learn the names in just a minute. So let's start by drawing that as an example. So 6 continuous sides like this. It looks like it's a little bit more elongated here, but you get the idea. This missing part of this circle, again, can't have curves or a missing part, so both of those would make that, or that both those things make that not work. This one has a curve to it. It has to be line segments only that can create it. So can't do that. This one, not the best drawing, but you get the idea, hopefully. And then we have a 5-sided figure here. This is called a pentagon. And so we're going to draw out that. Okay, and it has, again, all closed figure, all 5 line segments that create that polygon. This triangle also, triangles are considered polygons. This is our whole unit on triangles here. We're going to see more with that. And finally, this last shape we'll do more with in Unit 5. This is either a rhombus, or we'll talk about kind of how we can classify it later on. So kind of looks like, not quite like a square because it's on an angle. Okay, so that's all of those, and we just kind of now can see clearly, hopefully, what makes something a polygon now that we've kind of divided it into our 2 columns. So at the bottom here, it now classifies polygons by the number of sides. And so some of these you might have heard more often since you were probably much younger. 3 sides is a triangle. 4 sides is a quadrilateral. I know this diagram makes it seem like it's a trapezoid, but we will cover all the different types of quadrilaterals later. This is just, anytime it has 4 sides, it's called a quadrilateral. A pentagon has 5 sides, 6 sides is a hexagon, 7 sides is called a heptagon, an octagon has 8 sides, and a nonagon has 9 sides. And finally, we finish up with 10 sides, which is a decagon. There are more than this. 11 is called like an undecagon, 12 is a dodecagon, and so on, but you don't have to know all of these. But then we kind of generalize it and call anything that doesn't have a side to it, like let's call it n, we would just call it an n-gon. So if it was like a 20-sided figure, we would call it a 20-gon, and so on. So that's just something to keep in mind. If you have n sides, then it would be called an n-gon. Okay, now a regular polygon is equilateral and equiangular. So we know what equilateral and equiangular hopefully mean. Equilateral means all the sides are the same, and equiangular means all of the angles are the same, similar to what we kind of talked about in even Unit 2. And so when we know this piece, the regular polygons for each one, they would look like the following. A triangle would be an equilateral and equiangular triangle. The angle measures would all be the same, and the side lengths would be as well. So you can kind of imagine labeling it like this even. Same for a quadrilateral. It would have 4 congruent sides and 4, in this case it would be right angles, but they technically could be 4 angles that are congruent to one another. Same with pentagon and so on. So if you wanted to label all of this, all of the different shapes you can, I'm going to stop after the pentagon, but hopefully you get the gist of it, that all of the sides are congruent to each other and all of the angles as well. So hexagon, that's what it would look like. Heptagon, octagon is like the stop sign, and then nonagon and decagon. Notice how these were also nonagons, decagons, and so on, but these were not regular. That means that their sides did not have to all be the same length, and their angles inside don't have to be the same as well. But that's the case for these. Okay, so continue if you wanted to, again, put them all with the angles and the side lengths. You could definitely label them all, but you can always come back and do that as well. Okay, so next we have the triangle sum theorem. This is something you've probably been doing since middle school and didn't really realize that it had an actual theorem to it. This is also in your yellow packet now for Unit 4. It says the sum of the measures of the interior angles of a triangle is 180 degrees. Now I do have a proof here just proving why this works. You don't have any proofs on homework tonight. There's no proofs just yet. We're going to kind of lead into those starting after break, 4.2. So for the first part here, given that you have a triangle, it's called ABC, we have labeled it with numbers as well just to make it easy. You could have used just the letters even if you wanted to do that instead. But we're trying to prove that the 3 angles together add up to 180 degrees. Okay, so we have our given that it's a triangle. Now this step 2 has been put in for you because generally you don't have to do this yourself on a proof, but really what we want to do is try to create some parallel lines so that we can use the theorems from last unit, the if parallel lines then ones. So it says here, given a line and a point that's not on the line, they're talking about point D. So I'll put that in parentheses, D. There's exactly one line through the point parallel to the given line. So we want to draw out anywhere at all that with C, right? It has to be parallel to line AB passing through C because that's not on the line. And I have this other, actually let me be more clear here. This is referring to point C that's not on the line. You could also say it's point D, but since it's already drawn in here, let's draw line DC like this so that it's parallel. Now we know these 2 lines are parallel. I'm going to label it with that symbol, and now we can use any kind of theorems that we need to. Okay, so the first theorem has already been written in for us. If parallel lines and alternate interior angles are congruent, so let's see which ones are alternate interior. If it helps you to kind of extend the transversal so that you can see it a little bit more clearly, you can do that. And I also am going to write in a couple more angles here now that we've filled in these or made this new line. Let's put in an angle 4 here and an angle 5 here because that'll make it a little bit easier to identify which ones are alternate interior. So remember, these are my parallel lines. You can only have one transversal at a time. So if I'm just looking at this transversal, I have angle 4 and 1 are congruent because those are alternate interior angles. Or if I look at this transversal, I have 3 and 5 are congruent. So I'll write down both sets here. Angle 3 is congruent to angle 5, and angle 1 is congruent to angle 4. And the reason I'm doing that is so that hopefully later on it'll help me as I need to do some substitution. So we got that piece about parallel lines being alternate interior angles being congruent. I also see here that I have 3 angles that add up to 180, right? And so I can use those 3 angles to set them equal to 180 degrees and then use that, because it's not a linear pair, there's 3 angles here, but I can say if straight angle, then sum equals 180 degrees. Now, we don't use this one often. A lot of this proof, we haven't used any of these things. So again, like I mentioned, you don't have to do this on your proofs by yourself. So we want to say measure of angle 4 plus a measure of angle 2 plus a measure of angle 5 equals 180 degrees. I just used those three angles in any order to set those equal to 180. Okay, next we have, so now that we've said if straight angle, then we want to convert these other ones that were congruents to equals. So if angles congruent, then angles equal in measure. And the reason I'm doing that is so I can do some substitution in just a minute. So angle 3 and 5 are the same, and measure of angle 1 and 4 are the same. So now if I go back and I'm trying to make this equation look like measure of angle 1 plus the measure of angle 3, so I just need to substitute a few things in here. And actually I think I finished this in less steps than it said. So you can do substitution property, equality, and we would substitute in this 3 in for where it says 5, and we would substitute in 1 in for where it says 4, and that's where I can get right to measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees, and I don't need to write that there. So that could be one way to do this proof. Technically for step 5, since I substituted in the left-hand sides, I probably could have done symmetric property to switch them up first, and that would have made it 7 steps, but I'm okay with you guys doing just this. So this will not be on, a test or a quiz like this because it's just proving the actual theorem that we're going to use right now. So let's try out a bunch of examples here at the bottom using that theorem. Now that we know, it works, that we can just add up the three angles and have to equal 180. So definitely have a calculator as needed as you try these out. But we have this first one. You don't have to show work for these unless you want to. You can say 180 minus 65 minus 57 because we are subtracting those from 180, or you can add them up and then subtract from 180. But we have minus 57 minus 65. That comes out to 58 degrees. Okay, so measure of angle equals 58 degrees. Didn't really have a label there, so you don't have to write the label with it. You can put a letter if you want to or a number and then put that with the answer. The next one doesn't just have a triangle here. We're gonna kind of use a little bit more of our previous knowledge, prior knowledge of like linear pairs, supplementary angles, and so on. So these two angles here, 137 and the one in the triangle up here, those are supplementary because they're not a linear pair. So we want to first, from 180, you want to subtract the 137 to find its supplement, 137. And that comes out to 43 degrees here. And now I have part of this triangle, now I just need to find the other part, and then I can find its supplement again. And we are going to see a little bit more about, there's a theorem actually, we'll do this after a break, it's called the exterior angles theorem, that we'll see more of something like this where there's a shortcut you can kind of take. But for now, let's go ahead and just, from 180, subtract 102 and 43. And again, you don't have to show all the steps like I'm doing here. I'm just writing it so that you can all kind of follow. But this comes out to 35 degrees. But that's not the answer. The answer is where the question mark is, so I have to do 180 minus 35. And that is my final answer, 145 degrees. So the measure of angle would be 145. And finally, we have one more, and then the last page is just a practice page. I will have that answer key up as well so that you can check your answers once you've tried it out, hopefully. But this one here is vertical angles, 35 with this one here would be 35. And then these two angles would be 135. So you want to do 180 minus either 135, or I'm just subtracting each one at a time. So, 180 minus 135 is 45. So this angle is 45 degrees. Again, that's not the final answer. You need its supplement because it's a linear pair. So you want to do 180 minus 45 to get that this one here is 135. So final answer on this is measure of angle equals 135 degrees. I know those three did not have labels, so if you wanted to add in numbers or letters to name them, you could have done that. So that's pretty much it for 4.1. The main ideas, again, are just making sure you know what is a polygon and how to name them based on their sides. So if you don't know 5 sides of the pentagon. Make sure you memorize those. And then just using the triangle sum theorem to help you find missing angles. That's what homework will look like too. So for more practice though, go over to the next page and I'll have the answer key for that posted in Canvas.